In the previous lecture, we get here second section in chapter 4. We have scalar and vector fields here. In this section, we talk about only we only talk about scalar fields and vector fields. First, we have scalar fields. This is the definition of a scalar field. It says a scalar field is a collection of scalars assigned to each point in the domain of the field that satisfy the specific rule. A specific rule. Here we have given a rule is the scalar field satisfy it. We say a scalar field z equals to f of xy. It's in the xyz space. In xyz space, the scalar field is a surface. It's a surface, but in xy plane, it is a set of level curves. It is a set of level curves. In xyz space, it is a surface, but in xy space, xy plane, it is a set of level curves. And here we have the definition of vector field. We say a vector field, both have the same definition actually. For the scalar field, we say it's a set of scalars. But here, for vector field, we say it's a collection of vectors assigned to each point in the domain of the field that satisfies specific formula or rule. The vector field in xy space, in xy plane, is in this form. F of xy equals m of xyi plus n of xyj. We have only two components in the xy space. We have I and j. Okay, but in xyz space, we have three components. F of xyz is m of xyzi, n of xyzi, j, sorry, and p of xyzk. We have these three components, I, j, and k. For space, for xyz space, but for xy plane we have only two components, which are I and j. Scalar fields is a given scalar field phi of xyz. This is a scalar field. This is a scalar field. It's a function of xyz. There are two partial derivatives that involve scalar fields, which are gradients and directional derivatives. In gradients and directional derivatives, we have scalar fields. We work on scalar fields for finding the gradients and the directional derivatives. First, we have gradient scalar fields. For finding gradient scalar field, we use this rule. F phi of xyz to be a scalar field. It's a function of xyz. Scalar field phi of xyz is a function of xyz. We say grad phi, it's grad phi, and it's denoted by del phi. And this symbol is read as del or nabla. Okay, it's read as del, del. It equals to the derivative of the scalar field with respect to x times I, plus the derivative of the partial derivative of the scalar field with respect to y times j, and derivative of the scalar field with respect to z times k. Here we find that partial derivatives of the scalar field with respect to x, y, and z. We multiply the derivative with respect to x by y by I. We multiply it by I plus derivative of the scalar field with respect to y times j plus derivative of the scalar field with respect to z times k. This is the rule of gradient of a scalar field. This grad of scalar fields. Here, this symbol, when we say phi of xyz, it means this is grad f, grad phi, which is the gradient of the vector field. So gradient of a vector field is a vector field. We get a vector field in the result because here we have I, j, and k. We have components. We get a vector. You see, this symbol is noted by del or nabla. Okay. We say del operator in 2 dimensions, it equals to the partial derivative with respect to x times I plus partial derivative with respect to y times j. And we can write down as a vector. We write down it as partial by partial x, partial by partial y, and we separate them by a comma. And the gradient of f, del f, equals partial derivative of f with respect to x times I plus partial derivative of f with respect to y times j. It's in 2 dimensions, but in 3 dimensions we have 3 components, I, j, and k. So we take the partial derivative of the scalar field with respect to x, y, and z. Okay. Yeah. The gradient of y. Yeah. First, let's talk about this one. Del operator is partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and it could be written as this vector. And partial, so grad phi, which is del phi. Phi is a scalar field. It equals to the partial derivative of the function of the scalar field with respect to x, y, z. We multiply for x by I plus multiply for y by j and multiply for z by k. Okay. Now we have 2 examples. It says if f of xy equals to x squared plus y squared, find del f or grad f. Here we are going to find the gradient of f. F is a scalar field. At this point, so you should first find grad f, then we replace each x by 0 and y by 2. Let's find the gradient vector. Here, f of xy is for 1 equals x squared plus y squared. Find grad f at 0 and 2. We are going to find this. We must first find the gradient for the vector fields. We say grad f of xy equals finding the partial derivative of f with respect to x times I plus partial derivative of f with respect to y times j. Here we have only 2 components because we have f of xy. If we have f of xyz, in that case we must find 3 components, 3 partial derivatives. Here we have only I and j. So grad f of xy equals the partial derivative of f with respect to x is 2x. Is it? It's 2x I plus the partial derivative of f with respect to y is 2y j. This is the gradient of f. Now we must find the gradient of f at this point at 0 and 2. We say grad f at 0 and 2 is, here we replace each x by 0 and y by 2. So we get 0 I plus 4j, which equals to 4j. Sorry, this is j. It equals 4j. So this is the gradient for that scalar fields at this point. That's so easy. If you just know the rule, that's easy. but you should know the rule. Let's find the partial derivative of the function with respect to xy, because here you have f of xy, but if you have f of xyz, you must find three partial derivatives with respect to all variables. In the second one, we have phi of xyz. So here we must have three components, x, I, j, and k. So you must find the partial derivatives of phi with respect to x, with respect to y, and with respect to z. Let's find the partial derivatives. Let's first write down the function phi of x, y, z equals x minus 1 squared plus y minus 1 squared plus z squared. It says find grad phi. That means we must find the gradient for this scalar fields. At this point, it means we must find grad phi of 1, 0, 0. We must find this. So you first must find the gradient of the vector field of the scalar fields at x, y, z. We say grad phi of x, y, z equals partial phi by partial x times I. The derivative of the function with respect to x, we multiply it by I plus partial phi by partial y times j plus partial phi by partial z times k. Let's find these partial derivatives. We find the partial derivative of phi with respect to x, with respect to y, and with respect to z equals to grad phi, the partial derivative of this function with respect to x. These two terms, this one and this one, become 0 because you have no x in these two terms. You have only this term. The partial derivative of this term, x minus 1 squared, it's 2 times x minus 1. It's 2 times x minus 1. Is it? It's 2 times x minus 1. Times I. This is partial phi by partial x. And then partial phi by partial y. Finding the partial derivative of this function with respect to y, this term and this term becomes 0 because we have no y in these two terms. And the partial derivative of y minus 1 squared, it becomes 2 times y minus 1. J plus 2z k. Now we should find the gradient of phi at this point. We replace x by 1, y by 0, z by 0. We replace x by 1, y by 0, z by 0. And you get grad phi at 1, 0, 0 equals. If you replace x by 1, we get 0 here. Is it? We get 0 here. 0i. Because if you replace x by 1, we get 2 times 0i, or 0. Plus, if you replace y by 0, if you replace y, this is x, that's y, and this is z. If you replace y by 0, here we get minus 2 j. Okay, we get 2 times negative 1, which is minus 2j plus 0 k. If you replace z by 0, we get 0. It equals to minus 2j. This is the gradient for that vector field, for that scalar field at the point 1, 0, 0. The most important thing here is this rule. If you know the rule, others easy. So that's the answer for these two examples. We now have the geometrical representation of grad of f of x naught y naught. We say scalar field f of xy is a function of two variables. We have f of x and y. We have only two variables in it. Given us z equals f of xy. Geometrically, z is a level curves on the xy plane. It is z, which equals to f of xy, is a level curves on the xy plane. This vector, if we find the gradient of f at a point, at a specific point, we say it is a normal vector at the point x naught y naught. Normal vector at the point x naught y naught, which is orthogonal to the tangent line of the level curve set at that point. For example, let's say it's a level curve. We say the tangent line here is that, and the normal line is perpendicular to the tangent line, and it says it's orthogonal to it. It's orthogonal to the tangent line. Normal line is orthogonal to the tangent line. That means it's perpendicular to the tangent line. At this point, this is the normal line. This represents the gradient of f at this point, at x naught y naught. This is tangent, this normal line. This is tangent. It's only the geometrical representation of grad of a function of a scalar field at a specific point. The geometrical representation of grad of phi at x naught y naught. That means in R3, the gradient of a vector of a scalar field geometrically here w, which is grad of which is phi of x y z. It is sets of level surfaces in x y z space. But this vector is a normal vector to the level surface. W equals c. At this point here, it's the normal vector at the level surfaces. Now we talk about finding the unit normal vector by using the gradient of a scalar field. You should know how to find the gradient of a scalar field. Here we say it equals to partial phi by partial x times I plus partial phi by partial y times z plus partial phi by partial z times k. That's all. This is the gradient of scalar fields. And to find the unit normal vector, we say a unit normal vector could be obtained from the gradient of the scalar fields. It equals to the scalar fields dividing by its magnitude. We divide it by its magnitude. This is the magnitude of the scalar field. So here we must first find the scalar field. Sorry, the gradient of the scalar field. We get the vector. Then we work on that vector. We find its magnitude. Look, it says find the unit normal vector to the level surface. This is the level surface. It's phi of x, y, z equals x minus 1 squared plus y minus 1 squared plus z squared. It's the same as the previous example. Okay, it's the same as the previous example. Now, to find the unit normal vector, we apply this rule. In this rule, we must have grad phi at this point. We say we should find this first. We say from the previous example. -2, -2j. Yeah. Why do you need to change it? Just a moment. We will do it. Grad phi at 1, 0, 0, as you see here in the previous example, we found that's 2j. Grad phi at 1, 0, 0 is -2j. This is gradient of the scalar fields. Now we must find the magnitude. We must find the magnitude of it. We say the magnitude of grad phi at 1, 0, 0 equals the square root of, the sum of squares of all components. Here we have only one component, which is j, because other components are 0. I component and k component are 0. Here we have -2 squared plus 0 plus 0. This equals 2. This is the magnitude. -2 squared is 4. A squared is 2. Now we say the unit normal vector equals grad phi at 1, 0, 0 dividing by the magnitude of grad phi at 1, 0, 0. This equals to -2j dividing by 2. If you have more components, we divide each component by the denominator. But if we have only one component, which is -j. This is the unit normal vector that you get from that scalar fields. Okay, that's easy. Here you just need to know this rule. If you know this rule, then you already know that how to find the gradient of a scalar field, and also we studied how to find the magnitude of a vector, and that's all. Now we have directional derivatives of a scalar field. We say in finding the directional derivative, we must have the unit vector. Unit vector, okay? That means a vector which has magnitude 1. I mean, which is magnitude is 1. A unit vector is a vector that has magnitude is 1. I mean, that has magnitude 1. U is u1i plus u2j. The magnitude of u is 1. It's 1 because it's a unit vector. For any unit vector, the magnitude is 1. Okay. We have directional derivatives. Directional derivatives. F of xy at the point x0, y0 in the direction of the unit vector. In the direction of the unit vector is denoted by duf. That's denoted by duf, and duf equals f sub x dot u1 multiplying by u1 plus f sub y multiplying by u2. Here, directional derivative is a scalar function. It's a scalar field, actually. It's a function. we say duf, which is the directional derivative of f in the direction of u, in direction of the unit vector u, is f sub x times the first component in the unit vector plus f sub y multiplying by the second component in the unit vector. Here, the unit vector is u1i plus u2j. Okay, this is the first component and this is the second one. We multiply this by f sub x plus this by f sub y. Okay, and we get the directional derivative of f. And here we say since grad f is f sub xi plus f sub yj, we did it before. We say partial derivative of the function with respect to x times I plus partial derivative of the function with respect to y times j. So the directional derivative is the dot product. It is the dot product of grad f and the unit vector. Grad f and the unit vector. We can say it is that. Okay, as you see here, we say the unit vector is the gradient vector. The gradient vector is f sub x I plus f sub y j. And we find the dot product this with u1i plus u2j. We say the dot product of two vectors is the multiplication I with I components plus j with j components. That means we get f sub x times u1 plus f sub y times u2. We have no I and j here because I times I is 1 and j times j is 1. That's why we just get f sub x times u1, f sub y times u2. This is grad f and this is the unit vector. So the dot product of gradient of the function with the unit vector is the directional derivative. Or you can apply this. You can just write down that. We now have two examples. It says find the directional derivatives of z. This is a function. Z is a function of xy. In the direction of the vector, here we have given only a vector. It's not given that the vector is a unit vector. We must test it if it's either a unit vector or not. If it's not a unit vector, we must find the unit vector from this given vector. Okay? We say a unit vector is a vector that has 1 for its magnitude. We say the magnitude of A equals to what? Equals to 3 squared plus 4 squared. We just square all components. This equals to square root of 25, which is 5. Is 1? It doesn't equal to 1. That means this is not a unit vector. This vector is not a unit vector. And we must find the unit vector. We must find the unit vector from this given vector. How? We divide the vector by its magnitude. We divide the vector by its magnitude to get the unit vector. Have you studied it before? Let's write down the given information here. For example 1, I'm going to name this one, and this is 2. Okay. For 1, z equals 3x squared y, and a is 3i plus 4j. It says find the directional derivative duf duz at 1 and 2. We should find it. In finding the directional derivative, we must have two things: a function and a unit vector. But here we have given a vector, it's not a unit vector. We must find the unit vector from it. How? We say u equals a dividing by magnitude of A. We found magnitude of A is 5, is it? We say magnitude of A is square root of 3 squared plus 4 squared, which is 5. This equals to 3I plus 4J dividing by 5. So U, which is the unit vector, is 3 over 5I plus 4 over 5J. Here, if we find the magnitude of U, it must be 1. It must be 1. Look, let's check. The magnitude of U is, it's just for checking, 3 over 5 squared plus 4 over 5 squared. 3 over 5 squared is 9 over 25. And 4 over 5 squared is 16 over 25. We get 25 over 25, which is 1. And the square root is 1. That means its magnitude is 1. Here we get 25 over 25. And just for checking, you don't need to check if you do it correctly. Okay? So this is the unit vector. And this is Z. From the function, we should find the gradient of the function. Gradient of the function. We say grad Z equals Z sub X I plus Z sub Y J. Is it? As partial Z by partial X I plus partial Z by partial Y times J. This equals to derivative, partial derivative of Z with respect to X is 6xy plus partial derivative of the function with respect to Y is 3x squared. This is I. 3x squared J. Okay. We take the partial derivative with respect to Y. So partial derivative of Y is 1. And you get only 3x squared. Here, this is the gradient of that function. We find the dot product of U and this one. But here it says find it at this point. At this point. Where do we have X and Y? We have X and Y in only at grad Z. So you must find grad Z at 1 and 2. And then you find the dot product of U with this one to get the directional derivative at the given point. We say it equals to, we replace each X by 1, Y by 2. We get 12 plus 3J. That's it. Now we say the directional derivative of Z at 1 and 2 is the dot product of U with this vector, with the gradient vector. You say grad Z at 1 and 2 dot U, which equals to, let's first let's write down this one. It's 12I plus 3J dot 3 over 5I plus 4 over 5J. Here we multiply I component to I component plus J component to J component. That's all. This equals to duz at 1 and 2 equals 12 times 3 over 5, it's 36 over 5 plus 3 times 4, 12 over 5. This equals to 48 over 5. Directional derivative is always a scalar. Okay, it's not a vector. Okay. Yeah, we say I squared equals 1 and G squared equals 1. Because here I times I is I squared and you get 1. That's why you don't write down this. But I times J is 0. That's why we don't multiply this by that one. Okay, and j times I is also 0, even for k. So this is the directional derivative for the given function at that point in the direction of this vector. In the direction of this vector. That's all. And here you have another example. Do you have any question about that one? We have given a vector and a function. Let's finish that one, then okay? We have only this example. It's similar to the above one. Okay? We just need at most 5 minutes to finish it. It says find the directional derivative at 1 and 3. We have given the function of xy was e to the power x y squared. In the direction PQ, given that P is this point and Q is that point. When it says P to Q, it means at point P in the direction of Q at this point. Okay. Let's write down the given information. DUF at 1 and 3. Find DUF at 1 and 3. We have given the function which is e to the power xy squared. F of xy equals e to the power x y squared. From P to Q. P is negative 1 and 3 in the direction. From P, which is negative 1 and 3, to Q, 1 and 2, and negative 2. Here is all the given information for the example. What should we find? To get DUF, to get the direction derivative of f in the direction of u, you must have a vector and the gradient vector at that point. The gradient vector at that given point at 1 and 3. So let's first find grad f. We say grad f of xy. We must first find grad f at 1 and 2. Let's first write down the rule of DUF at 1 and 3. It equals to grad f at 1 and 3 dot u. U is the unit vector, but we haven't given the unit vector. We must find it from those 2 points. We say first, let's find this one. We say grad f equals it's at xy. It is f sub x times I plus f sub y times j. The partial derivative of this function with respect to x is itself, because the derivative of e to the power x is itself, and we have y squared which is a constant. It is e to the power x times y squared I plus partial derivative of this function with respect to y is 2 e to the power xy. This is the gradient vector. But the gradient vector at 1 and 3 will replace each x by 1 and each y by 3. Let's see. If we replace each x by 1, we get e to the power 1 times 9. We get 9. We get 9 e to the power 1 I. Or we just can write down e. 9 times ei. We replaced each x by 1 and y by 3 plus. Here we get 2ej. 2e times 3 is 6. 6e j. This is the gradient vector for the function at that point. Now we must find the unit vector. How to get the unit vector? We can get a vector from any 2 points. If you have given any 2 points, from a point to another point, we can get a vector. It's a vector. Let's say it's P and that's Q. From this to that, we can get a vector. How? We say, let's say V equals. It's a vector. We say it's a vector that we get from Q minus P. Q minus P. We say 1 minus 1. Okay? And -2 minus 3. Okay? Do you get that? Okay. We get 1 minus 1 is 2. -2, -3 is -5. This is a vector. If we write down as a vector, we get that 2i plus -5j minus 5j. This is the vector. Is it a unit vector? Is it a unit vector? No, it's not a unit vector. Why? Because the magnitude is 2 squared plus 5 squared, which is square root of 29. It's not a unit vector. Now we should find the unit vector. We say u from this, u equals v over magnitude of v. And the magnitude of v is square root of 39. It's square root of 29. We get 2 over square root of 29 I plus, so minus 5 over square root of 29 j. This is the unit vector. So we already found the gradient vector, and now we have the unit vector. We just find the dot product of these two, we get the directional derivative. We say duf at the point 1 and 3 is the gradient vector at the point 1 and 3 dot u. The gradient vector is 9e I plus 6e j dot u. U is 2 over square root of 29 I minus 5 over square root of 29 j. This equals, we multiply these two and these two. That's all. Yes, square root of 29. That's the magnitude. It's 2 squared plus 25. We get 18e over square root of 29 plus minus 30 minus 30e over square root of 29. And the result is, here we find the common denominator, which is square root of 29. We get minus 12 e over square root of 29. This is the directional derivative. Let me write down here. duf at 1 and 3 is minus 12 over minus 12e over square root of 29. This is the directional derivative at that given point. The directional derivative is at this point at 1 and 3 in the direction of u. It's in the direction of u. So that's all. It's easy. Okay, if you have given 2 points, we can get a vector from these 2 points. Then from the vector we can get the unit vector by dividing it by its magnitude. Do you have any question? So let's take a break for 10 minutes. We now have interpretation of directional derivatives. We say directional derivatives, DUF, is the slope of a tangent line. Is the slope of a tangent line. It represents the slope of a tangent line. Here, to find the slope of a tangent line, we can use directional derivative. So the directional derivative is the slope of a tangent line. And also, directional derivative of f is the rate of change of the function. It is the rate of change of the function at this point, at the given point. So directional derivatives can be used in finding the slope of a tangent line, and also it could be used in finding the rate of change of the given function f at the point x naught, y naught, z in the direction u, in direction of the unit vector. We now have maximum and minimum values of the directional derivative. We say the maximum value of the directional derivative is the magnitude of the gradient vector. This is the magnitude of the gradient vector. So here we just find the gradient vector and then its magnitude. It is the maximum value of the directional derivative, which is the magnitude of the gradient vector, and the minimum value of the gradient of the directional derivative is negative times magnitude of the gradient vector. Okay, here gradient vector, this is a vector, this is a vector. If you find its magnitude, you say that's the maximum value of the directional derivative. It's the maximum value of the directional derivative. And the minimum value, we just give a negative sign to it. Okay, these are the maximum value and minimum values of the directional derivative. And here, the unit vector could be obtained by this formula. We divide the gradient vector by its magnitude. We find the unit vector by dividing the gradient vector by its magnitude. Here we have given an example. It says find the maximum value of the directional derivative at -2 and 0 for this function, and state the direction of the unit vector as well. Here we should find the gradient vector, and then we find its magnitude. It will be the maximum value of the directional derivative. Let's find the grad f. Grad f at xy, it equals to f sub x times I plus f sub y times j. This equals to the directional derivative here. So the gradient vector for f is f sub x. The partial derivative of this function with respect to x is 2x e to the power y times I plus partial derivative of this function with respect to y is x squared e to the power y j. This is the gradient vector for f. And to find its maximum value, the maximum value of the directional derivative, we say the maximum value of DUF at -2 and 0. It equals to the magnitude of grad f at -2 and 0. Here we already found the grad f. We must find grad f at -2 and 0. We replace each x by -2 and y by 0, and you get minus 4i plus 4j. This is the gradient vector at the point -2 and 0. Then to find max duf at -2 and 0, we find the magnitude for this vector, for this gradient vector. So the magnitude equals to the magnitude of grad f at -2 and 0, which equals to the square root of -4 squared is 16 plus 4 squared is 16, which is square root of 32. And you can say it equals to 4 square root of 2, because it's 16 times 2. 16 can be checked out with the square root. We get 4 square root of 2. This is the maximum value of the directional derivative. This is the maximum value of the directional derivative. And then to find the unit vector and the direction of the unit vector, we say the direction, first let's find u. We said in the above, we said that u for the maximum, it is grad f dividing by its magnitude. We found grad f. We found grad f, which is -4i plus 4j. It's -4i plus 4j. This is grad f. So u is grad f at -2 and 0 dividing by the magnitude of grad f at -2 and 0. So it equals to -4i dividing by 4 square root of 2 plus 4j dividing by 4 square root of 2. These two and these are cancelled out, and we get -1 over square root of 2i plus 1 over square root of 2j. This is the unit vector. This is the unit vector. And it says, state the direction of the unit vector. We say the direction of the unit vector should be or must be in the direction of the gradient vector. We say that the unit vector is in the direction of the gradient vector. Gradient, which is gradient. The unit vector is in the direction of gradient. Okay, this is the answer for this example. It's only asking about finding the maximum value of the directional derivative at the point -2 and 0, where f of xy is x squared into the power y. And then it says state the direction of the unit vector as well. So the direction of the unit vector is in the direction of the gradient vector. That's in the direction of the gradient vector. That's all. It's always in the maximum value, and to find the maximum value of directional derivative, we say the unit vector must be in the direction of the gradient vector. Okay, and also the gradient vector must be in the direction of the unit vector. We now have properties of vector fields. F of x, y, z. This is a vector field. We say if f of x, y, z is a vector field given by this one, it's 3 components in R3, it's in space x, y, z. Then this operation has no meaning. It has no meaning. Okay, del f, del of the grad of the vector field, it has no meaning. For vector field, we say it has no meaning. But for scalar field, it is gradient. Okay, del of, let's say f. If f is a scalar field, if it's a function, we say it's gradient of the function, gradient vector for the function. But the grad of f is a vector. It has no meaning. This has no meaning. Okay. But we say we have two operations on vector fields. We have two operations on vector fields. If you have given a vector, then we have two operations on it, which are divergence as del dot f, del dot the gradient vector, del dot the vector field, sorry, it's vector fields. F is a vector field. We say divergence as del dot product with the vector fields. We find that a dot product between these two. And curl of the vector fields, curl of the vector field is the cross product of gradient or del and the vector field. We find the cross product of these two. What's this? In R3, this equals to partial by partial xi plus partial by partial yj plus partial by partial zk. This is that operator. That operator represents it. And f is a vector. It's a vector with given. We say divergence of a vector field, which is the dot product of del and the vector field, measures how the vectors in the vector field diverge or move further apart from each other. As divergence, it's going away from each other. But curl of the vector field is the cross product of del operator with the vector field. It measures the rate of circulation of the vector field around an axis. This axis is a normal vector that's perpendicular to the circulation plane. In fact, del cross product with f is said normal vector, and the magnitude of this cross product is its maximum circulation. So if you are asked to find the curl, you just find the cross product of del operator with the vector field. But to find the maximum circulation, we are going to find the magnitude for curl. Okay. Here we have two examples. It says find divergence of f and curl f for the given vector functions. Here, for finding divergence and curl, we must have given a vector field, not a scalar field. Scalar field is a function, but vector field has components I, j, and k. For the first one, let's say A. First, to find divergence. Divergence f of x, y, z equals del operator dot product with the vector field f of x, y, z. But first, let's find f of 1, 2, and 3. Okay, we say the divergence of f of 1, 2, and 3. It says find it at 1, 2, and 3. We must find divergence. Sorry, before that. So before we should first do the dot product, then finding it at that point. Okay, here I said before, and we talked about this before. Del operator represents, it's in three-dimensional. It's partial by partial xi plus partial by partial yj plus partial by partial z k. This is del operator. We say divergence of f of x, y, z equals, then dot product this with the vector fields. We have given the vector fields, which is this one. This x, y, z I plus y, j plus x, k. To find the dot product of these two vectors, we are going to multiply I component to I component, j component to j component, and z k component to k component. Yeah, we multiply this by that, and we get partial by partial x of x, y, z plus partial by partial y of y. Okay, then plus partial by partial z of x. That's all. Okay, that's all. Now we find these partial derivatives, this, that. When you multiply partial by partial x times this one, we get partial by partial x of the function. We find the partial derivative of the function with respect to x. This equals to the partial derivative of x, y, z with respect to x is y, z. Is it? Then for y, it's 1. And for this one, it's 0, because here we have no z, which equals to yz plus 1. This is divergence of f at x, y, z. Now, to find the divergence at the given point, we have given this point 1, 2, and 3. We replace each x by 1, each y by 2, and each z by 3 in the results. Here we get it's 2 times 3 plus 1, which is 7. So this is the divergence of this vector field at that point. Okay, it's how to find the divergence. We just find the dot product of the del operator with the vector field. And to find the curl for the given vector fields, we say curl of f is the cross product of del operator with f. We have del operator, which is partial by partial xi plus partial by partial y j plus partial by partial z k. And f is the vector field which is given. It's x, y, z I plus y j plus xk. To find the cross product of two vectors, we use determinants. We use determinant in finding the cross product of two vectors. We talked about this before. Okay, this equals to the determinant of a matrix. Here we have I, j, and k. Okay. We write down del operator components. Del operator is partial by partial xi plus partial by partial yj plus partial by partial zk. We write down I component beneath I, partial by partial x. And for j, we have partial by partial y. It's for del operator. And for k, we have partial by partial sets. And then the vector field, which is given, is x, y, z. We write down this beneath I, y beneath j, and x beneath k, beneath k, yeah, beneath k. It's x, y, z, y, x. Okay, since the vector field was given is x, y, z, I plus y, j plus x, k. Now we find the determinant of this matrix. You can use any method for finding this determinant by either writing down the first two columns, then doing the multiplication, or taking the first row and using cofactor. Here, we take this one, we get I, sorry, yeah, it's I multiplying these two and these two also. We multiply partial by partial y by x. We get partial by partial y by x. That means finding the partial derivative of x with respect to y. Then minus partial by partial z of y. When we multiply these two, we get partial by partial z of y. That's for I. Then for j, we remove these two. What's left? We have multiply these two minus multiplying these two. Okay, we get plus. So it's minus. It's plus, minus, plus. It's like that. We do it like that. We give a negative sign for the second one. Minus j partial by partial x times x minus partial by partial z times xyz. That's for j, for the second. And for the third one, we remove these two and you write down k plus k. We are multiplying these two, partial by partial x times y minus partial by partial y times xyz. Now we find these partial derivatives. The partial derivative of x with respect to y, this is 0. And this is also 0, is it? Since here we find the partial derivative, the function is x here. To find its partial derivative with respect to y, we get 0. And the function is y here. To find its partial derivative with respect to z, get 0. 0i minus the partial derivative of x with respect to x is 1 minus partial derivative of xyz with respect to z is xy. J. We have j here. And for k, we have partial derivative of y with respect to x. This is 0 minus partial derivative of xyz with respect to y. It's xz. K, which equals to minus 1 minus xy j minus xz k. Okay, and you can give this negative sign into the bracket and you get xy minus 1. Is it? You can give this negative sign into it, we get xy minus 1. This is j. This is the cross product of del operator with f. This is del cross f. This at xyz. How about the curl at this given point at 1, 2, and 3. We replace x by 1, y by 2, and z by 3. We say curl f, which equals to curl f at 1, 2, and 3 equals to del operator cross f at 1, 2, and 3. We replace each x by 1, y by 2, z by 3, and you get 2 minus 1 was j. Here we get 2 minus 1 is 1, and you get only j. Minus xz. 1 times 3 is 3. Okay, this is the curl of that vector fields at that point. And for the second, it's the same. The second one is the same. But here it's given as a vector. We should write down as the components. This becomes 1i plus x squared plus y squared j. Okay, do it by ourselves. Okay, but here for k component you have 0k. You should write down the third components. Yeah, because in the matrices, in the matrix, it must be 3 by 3, then we can find its determinants. So here we have 0 and 0. Both are 0. In that case, since we have no k component there, we write down 0k. Then do the same as we did. Okay. It's almost done. This is the del operator. Okay, and this is grad of phi. We talked about these, and here you have these properties of del operator. So the del operator of a plus b is del operator of a plus del operator of b. For multiplication, it's a times del operator of b plus b times del operator of a. For division, it's the same as the derivation of fractional functions. It's b squared denominator times del operator of the numerator minus numerator times del operator of the denominator. And here you have these operations about del operator. Now it's the end of this chapter, and see you for today.